What is peak water? Where are we on that timeline? Desalination is a technology that is a necessity for making fresh water in places that don't have it. Who is building it? Who can't afford it? And some life hacks that you can use to get fresh water today. In this episode of Life at 100 Megahertz, we explore the world water crisis.
When you buy an old house, you kind of expect a few creaks in the floorboards. You adjust, right?
Yeah.
You learn to step over the soft spots.
Right, yeah. It's just part of the charm, or so they say.
Exactly. But, there is a massive difference between a settling foundation and that terrifying moment you look down and realize, well, the floorboards are actually giving way entirely.
Yeah, it's a whole different thing. It's the difference between routine wear and tear and an acute systemic structural failure. The house isn't just aging anymore, It's collapsing under the weight of an environment it was just never designed for.
And unfortunately, that is exactly the reality we woke up to this morning. Today is July 2, 2026. And if you saw the news, you saw the grim headline out of France today.
It's just, it's horrific.
It really is. A historic heat wave just caused over 1,000 excess deaths. And temperatures there shattered records, pushing past 40 degrees Celsius. So for those in the U.S., that's over 104 degrees Fahrenheit.
And what we're seeing in France right now is the direct result of Europe warming at twice the global average. Their historical infrastructure, their power grids, those dense brick housing blocks, they simply were not built to withstand this level of sustained thermal stress. The materials themselves physically cannot shed the heat fast enough.
Yeah, the heat just gets trapped. But the mission of this deep dive isn't just to report today's bad news. We're going to take an incredibly detailed stack of sources, spanning global mortality models, the concept of peak water, cutting-edge laser desalination, and even the ancient engineering of desert cities, to really understand what our trajectory looks like over the next 10 to 20 years.
There's a lot of ground to cover.
There is. Okay, let's unpack this starting with the global baseline. Because how did we get to a point where 1,000 people die in a single week in a modern, wealthy nation?
So to contextualize the shock in France, we really have to look at the systemic global baseline that is already happening in the background. According to the Lancet countdown data in our sources, we're currently seeing an average of 546,000 preventable heat-related deaths annually.
Wait, 500,000?
Yeah, over 500,000. To put that into perspective, that is essentially one heat-related death occurring every single minute, globally.
1 a minute, every single minute.
Yeah.
And that is just the baseline for today.
Exactly. And the trajectory only accelerates from here. Looking at the World Health Organization's projections, heading into the 2030 threshold, they estimate climate change will cause roughly 250,000 additional deaths per year.
On top of the 500,000.
Right. And that calculation stems from just a handful of compounded factors. So Barrett heat stress, malnutrition from crop failures, malaria expanding its geographic range, and waterborne diarrhea.
Wow.
If emissions stay on their current track, multi-model projections show a staggering 370% increase in heat deaths by mid-century.
That level of physical stress creates an immediate economic crisis, too. The World Economic Forum is projecting $2.4 trillion in annual productivity losses by 2030.
Which is
It's massive. And it's a purely physiological limit. Outdoor agricultural and construction workers physically will not be able to safely work during daylight hours. The human body just cannot cool itself fast enough.
No, it can't. But the sources highlight a really crucial nuance here regarding global inequality. The planet might be warming as a whole, but it is definitely not handing out that risk evenly.
Right.
Over 90% of all premature heat-related deaths in the coming decades are projected to occur in low- and middle-income nations. Sub-Saharan Africa and South Asia are projected to suffer 10 to 15 times more deaths than wealthy regions.
10 to 15 times more.
Yeah. High-income nations like the U.S. and Western Europe will experience these horrific spikes during anomalies like we're seeing in France today, but they possess the capital to invest in HVAC infrastructure, grid resilience, early warning medical responses. Low-income nations just do not have that financial shield to artificially cool their environments.
I want to take us back in time for a second. Let's go back to the year 2000. Think the inconvenient truth era.
Oh, yeah. The early days of mainstream climate awareness.
Exactly. Skeptics back then constantly called the scientific models alarmist. But looking at the 2026 data in our stack of research, those atmospheric models from the year 2000 were incredibly accurate.
They really hit the bullseye regarding air temperatures. The models predicted warming of 0.15 to 0.2 degrees Celsius per decade. And today, we are firmly on that track, currently sitting at 1.45 to 1.55 degrees above pre-industrial levels.
Right.
Where the models of the year 2000 failed wasn't by being alarmist. They vastly underestimated how fragile the physical world was, specifically the oceans and the ice.
And our sources use a great analogy for this. I love this part. Scientists thought the oceans would act like a massive, dense thermal sponge, right? That they would soak up excess heat gradually over centuries.
Right, the slow absorption.
But instead of soaking it up slowly, the sponge got completely saturated almost overnight.
Yeah, the oceans absorbed over 90% of the excess heat, turning marine heat waves into a permanent fixture of the 2020s. And because that heat transfer was vastly underestimated, glacier melt just went exponential.
Which is what we're seeing now.
Right. The European Alps have lost 10 to 15% of their total volume just in recent years. Back in 2000, scientists thought major ice shelf collapses would take centuries. But the Larsen A and B ice shelves in Antarctica completely disintegrated in a matter of weeks.
Weeks, not centuries.
And the Thwaites Glacier is rapidly retreating right now as we speak.
So if the old models failed because they treated glaciers like static giant ice cubes sitting on a counter, these updated projections for 2026 to 2046 must be doing something radically different, right, to account for how ice actually moves.
What's fascinating here is that modern international modeling networks finally incorporate dynamic ice sheet physics. They simulate complex mechanisms like hydrofracture.
Hydrofracturing. Okay, how does that work?
So that is when meltwater pools on top of a glacier, cracks all the way through to the very bottom, and acts like a subglacial lubricant. It basically works like grease on a frying pan.
Oh, well.
It causes massive sheets of ice to slide off the bedrock and into the ocean far faster than simple surface melting would suggest.
Which gives us a much more aggressive timeline for the next 2 decades.
Sadly, yes. By 2036, models predict the first ice-free summer in the Arctic. By 2046, the European Alps will lose over 80% of their current ice volume.
80%. That's almost all of it.
And sea level rise will accelerate to 5 to 6 millimeters a year. But there's also a hidden physical consequence to this called freshening.
Right. I saw that in the notes.
As all this fresh water dumps into the ocean, it changes the water's density. Fresh water is less dense than salt water, so it floats like a lid on the ocean surface.
Oh, because it doesn't mix down.
Exactly. It prevents the normal vertical mixing of the water column. And that floating lid is permanently stalling the deep-sea conveyor belt that transports oxygen and nutrients globally.
You know, the terrifying part of these glaciers vanishing isn't just rising sea levels. It's that we are losing the literal water towers that billions of people rely on to survive.
The drinking water.
Yeah. And that introduces a concept in our sources called peak water. To picture it for you listening, imagine relying entirely on a checking account that is currently flush with cash.
Yeah.
You feel incredibly wealthy.
Right. You think everything's fine.
Exactly. But then you look closer at the ledger and realize the only reason the balance is so high is because your entire life savings is being drained into it all at once.
Yeah.
And there's absolutely no more income on the horizon.
And that phenomenon is occurring right now in the rivers originating in the Himalayas, the Andes, and the Rockies. We are living under an illusion of abundance.
Illusion of abundance.
Because these rivers actually have more water flowing through them today than they did historically. But that's just because the glaciers are bleeding out at exponential rates. Over the next 10 to 20 years, as those glaciers shrink past a critical mass, the runoff will precipitously decline.
The checking account will empty.
The checking account goes to zero.
The UN is warning that by 2030, global freshwater demand will exceed supply by 40%. The sources list massive populations: Lima, La Paz, northern India, Pakistan, western China. They are facing severe systemic dry season scarcity because those mountain water towers are running dry.
It's a looming catastrophe.
It is. So if the mountains are empty, humanity has to look to the oceans. We have to talk about the desalination revolution.
We do. But it is important to acknowledge the legacy problem first. Historically, turning salt water into drinking water was an ecological and climate disaster.
Oh, yeah. The documents point to a crazy cautionary tale from Saudi Arabia in the 1990s. They cite the old Jeddah desalination plant, which was famous for having 4 massive smokestacks burning heavy crude oil, just pumping out black smoke day and night.
Yeah, they were essentially burning fossil fuels just to physically boil millions of gallons of seawater.
Which is just wild to think about now.
It is. But in 2019, those liquid fuel thermal units in Jeddah were officially retired because the engineering strategy fundamentally shifted. The industry moved to seawater reverse osmosis, or SWRO.
SWRO.
Instead of using massive amounts of heat to boil water, SWRO uses 80% less energy by applying physical pressure to push the seawater through incredibly fine membranes, leaving the salt behind. They upgraded that plant to a high-efficiency natural gas grid, and newer mega projects outlined in the research, like NEOM on the Red Sea, are being built from the ground up to run on 100% renewable solar grids.
Okay, but here's where it gets really interesting, though, because the sheer technological leaps are wild. Our sources highlight a May 2026 breakthrough from the University of Rochester.
This is a game changer.
It really is. They developed a chemical-free direct solar thermal system using femtosecond laser-etched black metal.
It's a mouthful, but the science is amazing.
It is. So a femtosecond laser fires ultra-short pulses of light in a fraction of a second, so fast it doesn't even melt the metal. Instead, it blasts microscopic super-wicking grooves into the surface.
Yeah.
That textured metal absorbs 90% of incoming sunlight and violently evaporates a thin film of seawater the instant it touches it.
And the genius of that specific design is how it handles the remaining salt. Because normally salt just clogs everything up.
Right.
It uses fluid dynamics, specifically something called the coffee ring effect.
Coffee ring effect.
Yeah. So when you spill coffee, the liquid evaporates at the edges first, pulling the dark particles to the outside ring. The Rochester panels use that exact same physics to automatically push the dissolved salts away from the hot evaporation area onto a cold section of the panel.
That's so smart.
It prevents the system from clogging or scaling entirely without needing any toxic chemical pretreatments.
And for larger scales, engineers are deploying battery-free gravity units. They use solar power during the peak daylight hours to pump seawater high up into inland reservoirs. Then, when the sun sets and the solar panels turn off, gravity takes over.
Which is essentially free energy.
Exactly. The natural hydrostatic pressure of the water falling back down forces it through advanced graphene oxide membranes all night long. You get 24-hour desalination without needing massive, expensive lithium-ion batteries.
And the most important shift in this space is how we are solving the brine crisis. Because traditional plants harvest the fresh water and then dump a concentrated toxic sludge called brine back into the ocean. Because it's so dense, it sinks to the seafloor and suffocates marine life.
Just a dead zone.
Right. But now, two distinct frameworks are solving this. First, deep-sea modular desalination, like the ocean well models being piloted in California, they lower pods thousands of feet into the ocean.
And they use the extreme ambient pressure of the deep sea to literally crush the water through the reverse osmosis membranes for free.
Exactly the mechanism. And because they only harvest a tiny percentage of the water passing through the pod, the resulting brine is barely saltier than the ambient ocean. Plus, it's instantly diluted by fast-moving deep-sea currents.
Makes so much sense.
And the second framework is zero liquid discharge, or ZLD. Instead of treating brine as toxic waste, they treat it as an industrial gold mine.
Oh, this is the mining part.
Yes. They use a process called electrodialysis, which applies an electric current to pull the salt ions through a membrane, drying the brine into solid crystals. Then, they mine those crystals for the EV transition, extracting high-value lithium, magnesium, and commercial salt.
It completely changes the entire economic model. We're seeing massive construction hotspots deploying this tech right now. Saudi Arabia is building the Yanbu 4 project at $272 million. Egypt has their Water 2.0 initiative.
The scale is massive.
Chile is constructing the Antofagasta complex. That's a $5 billion project with 480 kilometers of pipelines pumping desalinated water up into the high desert for their mining operations. Even Texas has the $1 billion South Padre megaproject privately funded to protect the Rio Grande Valley.
But, desalination is a modern engineering miracle, but it comes with a strict geographic and economic barrier.
Yeah, that's the catch.
You need a coastline and a massive budget. Which brings us to the dark side of this transition, the billions of people who are being systematically left behind.
Because you simply cannot pump ocean water uphill into landlocked mountain nations like Bolivia or Kyrgyzstan.
It's just not physically or economically viable.
No. And the data for sub-Saharan Africa is grim. Water demand is projected to skyrocket by 163% by 2050, but large swaths of the region lack the capital and the electrical grids required to run reverse osmosis plants. Small island states are facing saltwater intrusion, meaning the ocean is seeping into their underground drinking water.
And outside of Tuvalu getting a migration treaty with Australia, most are just being ignored.
And then you have the megacity slums in places like Logos and Karachi, completely ignored by city planners and held hostage by water mafias who artificially restrict supply to price gouge the residents.
If we connect this to the bigger picture, this severe inequality is actively fueling the next wave of global instability. We are looking at water transitioning into a primary geopolitical weapon.
And I want to be incredibly clear to you listening. We are looking strictly at the intelligence and geographic friction outlined in our sources here. We aren't taking political sides on this show. We're simply reporting the physical reality on the ground. These tensions aren't necessarily about military invasions. They are about transboundary dam disputes.
Right. Upstream nations hold physical control over the flow of water. We see this vividly in the Nile Basin between Egypt and Ethiopia. Ethiopia is filling the reservoir of the Grand Ethiopian Renaissance Dam. By holding that water back to generate electricity, they physically choke off the downstream flow that Egyptian farmers rely on for agriculture.
Which is an existential threat to Egypt.
Absolutely. You see the same mechanism in the Indus River Basin, with India building upstream dams while downstream Pakistan faces climate-driven water bankruptcy. And you see it with Turkey controlling the headwaters of the Tigris and Euphrates rivers, drastically reducing agricultural flows into Syria and Iraq.
And when those agricultural systems fail because the water is shut off, migration is the inevitable result. Our sources note a very specific pattern to this movement. It starts with internal displacement, like herders in the Sahel losing their grazing land and moving into coastal cities like Lagos, which causes local clashes over land and resources.
Because the cities can't handle the influx.
Exactly. And once those cities are overwhelmed, it turns into regional spillover into neighboring developing nations like Kenya, or acts as severe border strain for southern Europe.
We also have to recognize the tragedy of lost aquifers as communities try to supplement this missing surface water. The documents outline a stark cautionary tale regarding Saudi Arabia's sweet water, known locally as Maya Helwa.
Yeah, the sources describe it as this incredibly pure fossil water that people used to fill up in big blue jugs at neighborhood stations back in the 1990s, mainly because it tasted way better than the desalinated tap water.
And that water was a geological wonder. Came from the ancient Araduma and Dammam aquifers. Millions of years ago, when the Arabian Peninsula had a lush, rainy climate, rainwater seeped deep into the limestone. It was naturally filtered, mineral-rich water trapped under immense artesian pressure.
Sounds amazing.
But during the 1980s and 90s, a massive agricultural boom pumped trillions of gallons of it to grow wheat in the middle of the desert. They literally pumped the aquifers dry. The physical pressure dropped, the natural springs stopped flowing, and the remaining water deep underground mixed with salt deposits and turned brackish.
So if governments and capital leave communities behind and the ancient aquifers are pumped dry, human ingenuity just has to take over. I want to shift from billion-dollar infrastructure to low-cost, grassroots survival hacks.
This represents the concept of appropriate technology. These are solutions that are cheap, require zero electricity, and rely entirely on local materials and basic physics.
The individual survival hacks in the research are fascinating. Take the classic Boy Scout solar still. You dig a hole in the damp dirt, put a container in the middle, cover the hole with a plastic sheet, and put a small rock in the center of the plastic.
Classic survival technique.
Right. The sun heats the ground, evaporating the brackish moisture in the dirt. That vapor hits the cooler plastic sheet, condenses into pure liquid water, and the rock funnels those droplets right down into your cup. And there are others too.
Like the toucan distiller.
Yeah, the toucan fire distiller for cloudy days. You boil dirty water in one can and use a hollow tube to catch the rising steam and funnel it into a cold cup to condense. There's vegetation wrapping, which works because plants sweat just like humans do.
Through transpiration.
Exactly. If you tie a plastic bag around a leafy branch, the sun forces the plant to transpire, and you capture that pure filtered water inside the bag. And they use a simple charcoal, sand, and pebble gravity filter to pre-treat muddy water before distilling it.
And communities are actually scaling these exact physical principles up. In the arid coastal deserts of Peru and Chile, they use fog catchers. They erect large vertical mesh nets facing the wind. As the morning fog rolls in, the microscopic moisture droplets trap on the plastic fibers, merge into larger drops, and trickle down into a collection gutter.
And it doesn't cost billions.
Not at all. A single net costs a few $100s, but yields 1,000 liters of pristine fresh water a day, literally out of thin air.
That's incredible. And for tropical slums, they use the water pyramid, which is basically a giant inflatable tent version of the Boy Scout solar still. For sub-Saharan Africa, they build sand dams. Instead of building a tall wall to hold a lake of water, they build a low concrete wall across a seasonal riverbed to trap heavy sand during a flash flood. That sand acts as a giant sponge, holding millions of gallons of water safely underground, entirely protected from the sun's evaporation and from breeding mosquitoes.
It's so smart.
And I have to mention the hippo roller. It is such a simple, perfect piece of appropriate technology. Instead of women carrying heavy 90-liter water barrels on their heads, which causes severe spinal damage over time, engineers turn the barrel itself into a wheel with a steel handle. It changes the physics of weight distribution entirely.
It is brilliant engineering, but we also have to look to the past to secure the future. Ancient engineering holds blueprints we are actively copying today. Look at Petra, the ancient capital of the Nabateans in Jordan.
The city in the rock.
Exactly. At its peak, it sustained a population of up to 30,000 people in a hyper-arid desert that received only 6 inches of rain a year.
And the documents detail their slow and divert philosophy. Instead of building one massive rigid dam to block violent winter flash floods, they built a 28-foot-wide bypass tunnel and a network of diversion dams to gently bleed the momentum out of the water and guide it into underground cisterns.
Working with the water, not against it.
Modern urban planners are explicitly copying this today with sponge cities, using permeable asphalt and local sunken parks to capture storm runoff locally instead of shedding it away through concrete storm drains.
The Nabateans also perfected passive gravity. They carved shallow channels for terracotta clay pipes, calculating the exact mathematical gradient to keep water flowing for miles without building up destructive pressure that would burst the pipe joints.
Wow.
They even utilized particle settling basins. They would let the dirty desert runoff pool in a wide, shallow carved basin so the heavy sand and debris would physically sink to the bottom. That allowed only the clean water at the surface to spill over into the drinking cisterns. We use that exact physical concept today in modern constructed wetlands.
That brings us to a more modern architectural experiment in our sources. Arcosanti in Arizona, designed by Paulo Soleri. While Petra mastered capturing rain across a vast, sprawling landscape, Arcosanti focuses on bounded density.
A different approach.
Yeah. It intentionally stops horizontal, leak-prone urban sprawl by building a compact, three-dimensional megastructure.
Arcosanti is designed around circular systems. They use an energy apron, taking the community's gray water from sinks and showers, and gravity feeding it directly into massive, south-facing sloping greenhouses to grow their food.
Closed loop.
Completely. They engineer passive microclimates utilizing massive concrete apses, which are essentially half-dome structures. These domes are angled precisely to capture the low winter sun to heat the concrete, but provide deep, cooling shade from the brutal high summer sun, drastically lowering evaporation rates. They even restored the nearby Agua Fria riverbank to catch floods and naturally recharge the local groundwater.
So what does this all mean?
The overarching lesson of both Petra and Arcosanti is miniaturization and integration. We cannot simply brute force our survival against nature by burning endless energy to pump water across continents. We have to work closely with the physical mechanics of the environment. Humanity is currently caught in a shrinking window.
It really feels like that.
On one side, we face the exponential reality of extreme heat and glacial melt. On the other, we are in a desperate race to adapt. We are simultaneously deploying hyper-advanced physics like femtosecond lasers and deep-sea hydrostatic pods, while being forced to relearn ancient passive desert survival techniques.
And it leaves us with one final provocative thought from the research to mull over. As we look toward 2046, we're seeing water become a highly commercialized commodity, where massive capital only flows to places that offer a financial return on investment.
Which is a terrifying thought.
If desalination plants and zero liquid discharge mining turn the ocean into a private mineral and water factory, and our literal survival depends entirely on this industrialized flow, who actually owns the water we drink? Will hydration in 20 years be managed as a basic human right? Or is the physical reality that it will become just another premium subscription service?
It is the defining economic and societal question of the coming decades.
And it brings us right back to that house with the failing foundation. We're realizing the floorboards are giving way. The solution isn't just to patch the wood. We have to fundamentally rethink the entire foundation of how we value and manage the most critical resource on Earth. Thank you for joining us on this deep dive. Keep questioning and keep learning.
I remember that sweet water in 1996 in the eastern province of Saudi Arabia. Some of the best water I've ever drank. And now today I'm hearing about aquifers in Utah drying up. Dry states are getting drier and wet states are getting wetter. I remember the 4 smokestacks over Jeddah, and I'm glad that they have cleaned that up. I believe that desalination is still the way to go. But not everyone can afford the cost of them. Will these people move somewhere else, or will they come up with their own solutions? Let's all learn to conserve what we have. Thanks for listening. Catch more episodes on lifeat100mhz.com.